Hello everybody, and welcome to page 145 in the workbook. This is the beginning of section 20.2, and in this section we're going to continue the discussion that we started about divergence of a vector field from the last section. Okay, divergence was about having some measure of the outflow of a vector field at a particular point. And what we're going to discover is that this leads us into something called the divergence theorem, which is a convenient way of calculating a flux integral in a particular situation. Okay, and to understand the divergence theorem, we need to first think about flow through a closed surface and just some of the properties that it has. So we'll lead into this theorem with a couple of illustrations here, starting with the preliminary illustration below here. And let's read this together. Okay, so we're going to let S be the outside surface of a solid region, and in particular, it's going to be the solid region shown here in figure 1. It's two cubes that are glued together. The arrows that you see in the picture are just the vector field F, okay, that's flowing through this surface. And what we're going to be interested in is the flow coming out of this surface, the flow of the vector field F out of the surface. Okay, so just to give names to some of this stuff, let's let S be the surface of the whole solid. That's just our name for the figure that we're seeing to the right. And the question that I'd like to ask is, how many different panels are there on the outside edge of this surface? And when I say panel, I mean a square panel. We can kind of see those in our picture. Okay, so let's note a couple of them together. There are a couple of panels on the top, okay, namely this one and this one that I'm highlighting. Those are two surfaces, outside surfaces through which our vector field could flow. And then there are another two panels on the bottom. Those are also on the outside of S. So we're up to 4. What else have we missed here? Well, there are some panels on the front and the back. Okay, so 2 on the front and then 2 on the back. So now we're up to 8. And have we missed any? Any other panels on the outside of S? I can think of 2 that we've missed, the right side and the left side. Those are also on the outside of S. Okay, so altogether, there are 10 faces, I'll call them, and those are just my name. That's just my name for the outside panels of the surface through which our vector field flows. Okay, so here's where it gets a little bit interesting. Now we're going to imagine that we take that surface S that we started with, and let me just get rid of the markings that we have here. And imagine that we take that surface and we pull it apart into 2 separate cubes. So we're going to think of this as a dividing line, and we're going to split it, break that surface S apart into 2 cubes, and I'm going to give names to those cubes. We'll call them S1 and S2. S1 is going to be over here, and S2 is going to be over here. Okay, so we'll just say surface of the left cube, and S2 is the surface of the right cube. Okay, and here's the question I want to ask you. After we've pulled those 2 apart, now we've got 2 separate cubes sitting in front of us. How many faces do those separate cubes have? Okay, well, because they're cubes, they should have exactly 6 faces: a top, a bottom, a right, a left, and a back and a front. So what's interesting is by pulling that surface S that we started with apart, we actually created 2 new faces on the outside. Okay, we've got 10 up here, and then together between the 2 we've got 12. All right. And so what we want to study here now is the relationship between flow through S and flow through these 2 smaller surfaces, S1 and S2. And I'm going to start by writing down an equation, see what you think about it. So I claim that the flux through S, this 10-phase surface that we started with, is exactly equal to the flux through the left-hand cube plus the flux through the right-hand cube. Okay, now I'm hoping that you might be a little bit skeptical of that equation because of the fact that if you count faces, we've got 10 outside surfaces for S, but S1 and S2 together have 12 outside surfaces. So how could this equation be true if the number of outside surfaces don't line up? Okay, very good question. Well, one way to think of it, to reconcile this, is to sort of think about what happened when we pulled the surface apart. So here was the place where we split S into S1 and S2, so there was the shared wall between those two surfaces. And that shared wall that I'm highlighting, that became the right-hand surface of S1 and the left-hand surface of S2. Notice what our vector field is doing on that surface. It's going left to right according to our picture. Okay, so I want you to imagine that maybe you're sitting over here in S1, so there's you, and in S2 is your neighbor. And ask yourself, how would you in your neighborhood see that flow, the flow of the vector field? Well, you would look at it and say, there's flow going outside of my cube, and so it's going to be positive because we've chosen the outward orientation. So as far as you're concerned, the flow along this wall is positive, but what would your neighbor say about that? Your neighbor would look at that and say, no, that flow is negative, it's coming into my cube. And so what ends up happening is when you add these two things, that shared inner wall, you're going to say it's positive, your neighbor's going to say it's negative, and they're going to cancel. And so you get the exact same thing, winds up canceling out, and the flux through S is going to be the same as the flux through S1 and S2. Okay, we could summarize that maybe by just making a note at the bottom of this. So this equation that we labeled star above is true because, and I'm just going to put in words the observation that we made above, the flux through that shared inner wall in the above figure cancels. Okay, it's positive for you, it's negative for your neighborhood, and so we get a net of 0 when we add the two together. Okay, just to rephrase that. Okay, it counts as positive flow for S1 and negative flow for S2. Okay. Turns out this is a key observation in formulating the divergence theorem, and in the next video we'll look at illustration 2 and put this observation to work for us.